Modes of failure and factor of safety are the topics that we are going to study. See, in design, we have a lot of considerations. Modes of failure is also one of the important design consideration we must anticipate. When we design a machine element, we must be able to predict in what mode does the component may fail for the given set of service conditions in which it is going to operate. So if you have a feedback system like that, your design will improve. Okay, and why do we use this factor of safety in our design calculations? What is the idea behind it? We shall discuss that today. Modes of failure. Let us understand the meaning of failure. So failure means if a component is unable to perform its intended function satisfactorily, it is a failure. And we are going to look at the mechanical failures of components. So the mechanical failures are basically classified into three categories: failure by elastic deflection, failure by general yielding, and failure by fracture. See, if you are applying a mechanical load onto a component and it is deforming elastically, and if that magnitude of deformation exceeds a certain limit, it may not allow the component to function, right? Then we call it as failure by elastic deflection. Similarly, failure by yielding. So the component is entering into the plastic zone, that is the cross sections. All the fibers in the cross section of the member started to yield. So when it loses its shape, again it cannot perform its intended function. And failure by fracture. When the component disintegrates physically, obviously it won't function, right? These are a few examples, okay? So where we have to focus on the design criterion. For example, while you design a transmission shaft, which is basically used for supporting gears, right? So they do support gears. So what will happen? It will deflect. There will be a transverse deflection. That is bending, right? So you will have only elastic deflection. Usually shafts are not permitted to have plastic deflections. Otherwise, the gears will simply sag down and you cannot transmit power. So the elastic deflection will have a limit. So you must ensure that it won't go beyond that. Well, if such is the requirement, what is the physical property or mechanical property we should look into? See, we looked into previous slides of mechanical properties of, right, various mechanical properties. Can you guess what is the mechanical property, right, that we must look into now? It is actually lateral rigidity or torsional rigidity. We must look into as the design criterion. That is GJ, right? If it is subjected to only bending, we will look into flexural rigidity, that is EI. Okay, so we must select materials with high values of EI or GJ. Okay, so for every failure mode, we will have a corresponding governing criteria, design criteria. So that is actually your mechanical property. So that is where we have to look into. Then elastic deflection can also result into unstable conditions like buckling, right? See, buckling is simply the lateral deflection of a column subjected to compressive loads, or it can lead to vibrations also. So in such cases, we will look at the permissible lateral or the torsional deflection. We will set the limit onto this. What is the criteria, design criteria? Again, the same rigidity only. Okay. Usually for design of components restricted by elastic deflections, we look into the stiffness. Okay, so it should be it should have enough stiffness because you know the meaning of stiffness. Stiffness means resistance to deformation, elastic deformation. Higher the stiffness, lesser the elastic deformation. But we may not look into the types of stresses induced or any other mechanical properties, right? So we focus on the limiting criterion and the design criterion. So modulus of elasticity and rigidity. Suppose if your component is subjected only to axial load, then you must select a component with higher modulus of elasticity, because elasticity means stiffness, right? Now that is about failure by elastic deflection. Now let us come to the second category, failure by general yielding. For example, you have employed a ductile material in your machine element. When will it lose its functionality or its usefulness? Obviously, when it enters into plastic zone, right? Because it starts to lose its original shape. Then it cannot deliver its function. So there are two types of yielding. One is, we call it as general yielding, and then local yielding. In general yielding, we mean that the entire cross section is subjected to plasticity. Okay, that is what general yielding. We focus only on general yielding. And in localized yielding, only a selected portion of the component will be subjected to yielding because of stress concentration. Right, you will have a localized concentration of stresses due to some reasons like material discontinuity, voids, or any other defects, and geometric discontinuity. There is a sudden change in the cross section. So like we will discuss this in separate chapter in detail. Okay, so as of now we will focus on only general yielding as our design criterion. In components were subjected to plastic deformation, you must ensure that the stresses induced in the component do not reach yield strength. That's all in this case. Whereas in the previous case, the deflection, elastic deflection, must not exceed the specified limit. That is it. And the corresponding mechanical properties we look into is rigidity and stiffness related properties like torsional rigidity, flexural rigidity, or elastic modulus based on the type of load to which the component is subjected to. In this case, we look into the yield strength. Okay, so it is an important property for designing against failure due to general yielding. Suppose if your component is made up of brittle materials, when will it cease to function? Probably when it fractures, because it cannot undergo any significant plastic deformation, right? So then we cannot use yield strength, because for brittle materials you would have seen from the stress strain curve, the yield strength and the ultimate tensile strength and fracture point, they lie very close to each other or might overlap also. Okay, so when such is the situation, we use ultimate tensile strength of the material as the design criterion. Okay. And in case of brittle material, the failure will be sudden and total, that is catastrophic. So now that we have looked at the failure modes associated with only axial bending torsional. Okay, so if it is subjected to dynamic loads, yes, we will discuss that in unit 2. As of now, this much is needed for this particular chapter. Then let's come to the factor of safety. What is this factor of safety? You have studied this in mechanics of solids a lot, right? So we are just recapping it because we will employ these things in our problems. It is simply the ratio of two quantities which have the same units. Strength by stress. You would have calculated like, right? Working strength, maximum strength by working stress or allowable stress. Isn't it? As I said earlier, strength is the maximum stress that the component can withstand without fracture, whereas stress is any value which is less than the strength. Then critical load by applied load. Critical load, this you would have used in buckling. And the applied load, failure load by expected service load. Maximum cycles by applied cycles, this is in case of fatigue. Maximum safe speed by operating speed, this is we will design in whirling of shafts to find the natural frequencies. Okay, so this you will study in mechanical vibrations. So factor of safety is basically the ratio of two quantities which will have same units, and hence it is a unitless quantity. So for example, these are the things you would have employed in your mechanics of solids, and we will continue the same in design of machine elements also. Why do we use it? See, because of the uncertainties involved in calculating certain factors related to design. What are they? Do you know the exact value of the external load acting on the component? Definitely not. Because see, in your academic problems, everything is given to you. So you know the exact value of the load, 50.00 kilonewton, deformation, 2 microns or 4 microns, temperature, right, XYZ, Kelvin or temperature. Everything is precisely given to you. So you can use the theoretical models and solve it. Whereas in reality, it is very difficult to calculate the magnitude of the external load. You have a building, let us assume. Can you tell me the different loads that acts on the building? Sometimes seismic loads also can act. What is the magnitude of it? That is a dynamic load. We don't know. Impact load, wind load, right? And self weight. People will keep moving up and down. Weight due to the people, right? They are all the dynamic loads. So different static and dynamic loads, identifying magnitude of it, very, very difficult. So there is an uncertainty related to the magnitude of the external and material property, right? See, in all our theoretical calculations, we say that we have certain assumptions, right? Only under those set of assumptions we can use our theory. You say material is homogeneous, isotropic, right? And so on. So, but do you know that the properties are same in all the directions? We don't know. We are not sure about it. So there is uncertainty, variations in the dimensions of the component. Say in our case, in the problems what we solve in academics, we use simple geometries like rectangular, circular, everything. But in real component, the cross section is intricate. So how do you calculate the cross section and the variations of it? Again, there is some uncertainty. Okay, but now that you have advanced numerical tools, you can calculate the stress at each and every point. Okay. However, there is some uncertainty. In order to simplify the calculations and to account for all the assumptions we make in design and analysis, right, and to account for the uncertainties associated with the load, material property, and variations in dimensions, we employ factor of safety, right? I don't know all these things. So what I do is I'll simply apply this factor of safety. Okay. Suppose if the load acting on the component is, let us say, 100 kilonewton, you are saying 100 kilonewton, but actually in the service there could be only 50 or 60 kilonewton, right? Then what is the factor of safety? 100 by 50, so 2 times. So magnitude of factor of safety, how to choose it? So it depends on the case. We shall look into that. Effect of failure. See, if the failure mode is if the failure mode results in substantial financial loss and loss of human life, then we have to select a higher FOS. Higher means what is the magnitude of? Is it 100, in the order of hundreds, thousands? No, it will be usually in single digits only, and mostly it will be less than 5 only, not beyond that. Okay. So you have to select high FOS. FOS will never exceed 5 or 5. Okay. Type of the load. If you have a static force, the load application will be very, very gradual, slow. So you can choose a small FOS. Dynamic loads, the after effects will be very dangerous. So we will select higher FOS. Degree of accuracy in force analysis. If you know that is what force exactly, then you don't need to use a higher FOS. Okay. Similarly, material. For ductile materials, we use low FOS based on yield strength because it will give sufficient, it will give warning as it undergoes sufficient plastic deformation. Whereas for brittle materials, failure is catastrophic. So I have to employ higher FOS, okay, based on the ultimate tensile strength. And then reliability. So we had seen the definition of reliability in the earlier classes. Let me reiterate it. Reliability is the probability that the product can or system can deliver its function uh, within the specified period of time safely. Okay, so this is what reliability means. It is basically the probability. Okay, higher the probability, higher the reliability. Probability of what? Probability of functioning. Okay, so if you want higher reliability, for example, in applications like power stations, defense equipment, we need higher reliability. So higher FOS is required. Another consequence, see, when you go for higher FOS, thing is the cost will also increase because you are adding material, more material into it. When you add more material, what are you ensuring? You're ensuring that it can carry more and more load, right? Beyond what is required. This is what we call it as deterministic approach in design. We are not accounting for the random variations. So we deal with only deterministic approach in the whole DME codes 1 and 2. Service conditions. So when it is likely to operate in harsh ambience like corrosive ambience, high temperatures, very, very high mechanical loads, we have to employ higher FOS. Quality of manufacture. If it is very good, yes, you can go for lower FOS. So this is about the reason for including factor of safety in our design and the various factors that govern the selection of the magnitude of factor of safety. These are the references I have used. Thank you.